Okay, so let's get on with the next part of the lecture, where we are now going to move on to chapter 2. Chapter 2, if you look into the book, it deals with tensors and vectors and tensors and related mathematics. We will also be dealing with those, but I will also include some other aspects of mathematics that will be a bit useful. Much of this is very simple and something that you have probably come across, but still this would serve as a good revision for you guys. So for the first thing we'll start off with is the Leibniz rule. Now Leibniz rule deals with differentiation under the sign of integration. So the question is, for Leibniz rule, if you have to take the derivative, where let's say you have derivative with respect to x for an integration, where the dummy variable here or the variable for integration is t. So the question is, why are we taking derivative with x? Well, that's because the upper and the lower limits that are variables now, and the question is, how do you evaluate that? The answer to this is that this can be evaluated as the function evaluated at v of x with multiplied by the derivative of dv dx. So vx is the upper limit. So here inside the function is now so this is now f of v of x, and here this is the derivative of v with respect to x, and this minus f ux du dx. Okay. If you want to prove this rule, it's rather straightforward. So if you want to do that to prove this rule, let us consider f to be the antiderivative in this case. So capital F is the antiderivative, which means that I can write f t dt with these ux and vx as f of vx minus f of ux. Right? So f is the antiderivative of small f. Capital F is the antiderivative of small f on a given boundary or a certain within a certain bound, and within this the vx and fx vx and ux are within those bounds. Okay, so I'm not writing down all that. If you want to look back at this, then all you need to do is to consult one of your maybe the high school calculus books, and that will have it. So now if you want to take the derivative, so this implies that if I take the derivative of my left hand side, then you end up with the derivative of f. So this is v, but this is v of x. So I should just write the whole thing, v of x dx minus df ux by dx, which is, by applying chain rule, you can straight away write the RHS is therefore equal to f v of x dv dv dx minus f ux du dx. Okay, so our rule has been proven. Okay, so this is the important rule. that you need to know? Okay. Okay. Where will we use this? We'll come to that. Okay. So everything that I'm going to go through, there is some usage somewhere. But for this particular one, we'll come back later. Okay. Now, let's say we'll also want to look at multivariable functions and partial derivatives. Okay. So by multivariable functions, we mean functions of the type f, where now f, which was in the earlier example, which is a function of only one variable, let's say it's a function of two variable, f x comma y. Okay. So if you have a function like this, and if let's say we are moving from a point, and we move from point x naught comma y naught to x naught plus dx and y naught plus dx, then the total differential of f can be written as del f del x evaluated at x naught comma y naught multiplied by dx plus del f del y evaluated again at x naught comma y naught multiplied by dy. And the way this, I mean, there are many ways to prove this. Well, so I'm not going to go through all of them, but I'll just suggest that fxy can sometimes be linearized the spelling is incorrect, linearized and replaced with this linear equivalent in a when you are in a small neighborhood of a particular point, and let's say f l x comma y is that, and that can be written as f x naught y naught plus del f. So the linear, okay, let me first write down the expression and then I'll explain. Okay. Evaluated at x naught y naught x minus x naught plus del f by del y. Okay, I'm running out of space. Let me write it. Del f by del y evaluated again at x naught y naught, and this is y minus y naught. Okay. So okay. So what I'm doing here is, this is the function, okay, and let's say we are in the small neighborhood of x naught y naught, then sometimes this function can be linearized, and this function is also called the standard linear approximation of f at x naught y naught, and in that case you can write it as f x naught y naught plus the first partial derivative of f with respect to x evaluated x naught y naught multiplied by x minus x naught, and df del f del y again evaluated at x naught y naught multiplied by y minus y naught. So you can see that, and you can show that the error for this decreases as you shrink the as you come closer and closer to x naught and y naught, and you can get to this differential, this particular form from there, or you can approach it from other means. Well, why are we doing this? The reason being, let's say you have a volume, let's say you have a cylinder, and the cylinder has radius r and height h, and somebody is asking you to calculate the volume of this cylinder. Okay. So the volume of this cylinder is going to be pi r square h, obviously. So now if I have to figure out what is, okay, let me first write the expression. So let's say dV now, going by the previous formula, is del V by del R at evaluated at some r comma h multiplied by dr plus del V by del H evaluated again at some r comma h into dH. So basically my dV is 2 pi r h into dr plus pi r square to dH. Great. So let us say that you are facing an engineering problem where you have this cylinder and you are trying to measure the volume with respect to the measured variables, which are using the measured variables, which are r and h in this particular case. Now, whenever we do any experiments, we always have experimental uncertainty. So let us say that we have, so let us say that there is an experimental uncertainty in R which is 2% or less than that, and there is an experimental uncertainty in H, and uncertainty in H which is less than equal to 5%. Okay. So the problem at hand is, because these are the experimental variables R and H, you have an uncertainty. Now the volume of the cylinder is being calculated on the basis of these measured variables. So what is the resultant uncertainty when you calculate volume? Okay. So what is the resultant uncertainty? In V. Okay. Now it's given to you that R, the uncertainty in R is less than 2%. What does this imply? This implies that dr by R is less than equal to 2 into 10 to the minus 2. Similarly, the uncertainty in H is being given to you as being less than equal to 5%. So dH by H is less than equal to 5 into 10 to the minus 2. So right now, what is V? So by the way, we just calculated dV. To calculate the uncertainty in V, all we need to do is the relative uncertainty. We just need to divide this by V. Okay. So now dV by V becomes 2 times, it's rather straightforward to do this division, 2 dr by r plus dH by h. From here I can write that the absolute value of dV by V will be less than equal to 2 times dr by r plus dH by h, which for my case is 2 into 2 into 10 to the minus 2 plus 5 into 10 to the minus 2, which is 9 into 10 to the minus 2. So, resultant uncertainty in V is less than 9%. Now, this is one way to estimate. A lot of people, so see, this 2% is an error, which means it can be plus or minus 2%, and similarly here it can be plus or minus 5%. Some people prefer to estimate this using RMS values. So, if you want to use that, then dV by V will be equal to square root of 2 dr by r square plus dH by h square, or basically less than equal to. So, this is the RMS estimate of, so this is the root mean square estimate for the error. This will be rather important when you do a lot of the fluid mechanical calculations. I have obviously shown this to you using a rather trivial example of a cylinder volume, but these can quickly become very much complicated for many experimental observations. For example, when you are measuring the mass flow rate of fluid volume using certain quantities, or estimating some of the other important fluid mechanical uncertainties, related uncertainties. So, I have just shown this to you with a simple example, but this can, the functional form here can become more complicated, and then you have to use the appropriate, you have to do the appropriate analysis yourself. Okay. So, this turns out to be a very important analysis, and it is also called the propagation of error analysis, which has to be done quite a bit when you are doing experimental work. Okay. So, the next thing we want to look at is again some. So, we are reviewing a lot of calculus right now. So, another thing we look at is the chain rule. So, remember when you had a simple function, let us say h, which is a function of a single, which is equal to f of x, where f is just a function of a single variable, and if we had to calculate the derivative of h with respect to some other variable, let us say t, then what was the chain rule? It was simply dH by dt into dt by dx. Okay. So, it almost appears as if these two are cancelling, and that is what it looks like, but that is not how this rule is arrived at, but it almost gives you that feeling that this is almost like a fraction. Okay. So, now we ask the question, what happens if f or h, sorry, so h becomes a function of two variables. Okay. Then how do you do the chain rule? So, what is the appropriate formula for that? So, again the question is, I have to, let us say, take the derivative of h with respect to another variable, let us say t in this particular case. Then you have to take the derivative of the partial derivative of f with respect to x first, and this is multiplied by dx by dt, and you have to take the partial derivative of f with respect to y, and then you have to do dy by dt. And this goes on. So, if you can easily make h to be a function of, let us say, 3 or more variables, and then you will, if you have this kind of, if h is of this form, then it just goes on. You do the same thing all over again, and you will have del f del x dx dt, del f del y dy dt, plus del h del z dz dt. So, obviously, here x, y and z are functions of time. So, that is why you are able to take these derivatives. So, let us say you have a variable which is, so let us say, okay, maybe I will just use a new page. So, let us say that you have a variable which is a function of, so let us say we have capital T, or should I just use h, since I have been using that? Okay, maybe I will just use that way. Okay, let us say you have a variable h which is a function of time x, y and z, where these x, y and z are also again functions of time. Okay. If you have a situation like this, then if I have to take my derivative of h with respect to time, how do I calculate that? Well, I just go ahead and apply my chain rule, which will give me a del h by del t, and then you have a del t, so that we do not have to write that. So, let us write the other terms, which is, oh sorry, you have del h by del x into dx by dt plus del h by del y dy by dt and del h by del z dz by dt. Okay. Okay. There is a good reason I am going over this, and perhaps some of you have already been able to recognize this derivative on this side, and we will come to this in chapter 3 when we start work with the kinematics. Okay. So, you can see how that so we will see when we reach chapter 3 that this will be of quite importance to us. Okay. So, now the next topic that we will go to are vectors and tensors. Now, for a lot of you, some of you at least, your recollection of what is a vector may be something like this, where vector are arrows. Okay. And the vector, if you had to add vectors, then what did you have to do? Well, you used to take two vectors, let's say these are what has to be added to each other, then you had a parallelogram law, and the parallelogram law would give you the resultant vector, right? Is that something that resonates with you? This is how most of us learn vectors when we are in school, or sometimes even in college, that we learn vectors are arrows, and that if we have to add these things, then we have to use the parallelogram law. And if you have to multiply arrows by numbers, including plus, minus, so if you have to multiply the number by the vectors by scalar quantities, then you measure the length of this arrow, and then you just multiply that length and you extend that arrow further, right? So these are the operations that we have been usually familiar with, but this is something of an old knowledge. Okay, so this is well, I shouldn't say this is old knowledge per se so much, but rather a simplistic understanding of. Okay, so this is a simplistic understanding of vectors. So in order to understand this topic in a little bit more depth, and one of the reasons we require this depth is because we are now going to be, we will now start dealing with even more complicated quantities. Right? So one of the things is we will be dealing with vectors and even tensors. And tensors will come up in the very next chapter, which is on kinematics. So initially we are used to, let's say, the quantity u being a velocity, and we used to putting one bar over it. When you have a tensor, for example, stress, okay, I was using tau earlier, so I'll just keep using tau right now. Then maybe we'll add two bars to denote that they are tensors. To understand tensors properly, we have to go into a little bit more abstraction with regards to vectors themselves. And unless we do that, we might find it difficult to understand the more complicated topics in this area. Okay, so I will be introducing you to a slightly more abstract idea of vectors itself. And before we do that, I will introduce to you an even more a basic requirement of being able to go on to vector spaces, and those are called fields. And I assume that all of you are familiar with what are real numbers and complex numbers, and so that part is sort of assumed. And the next set of discussions that we'll have, we'll just assume that this is basically for all real numbers or complex numbers. So if, let's say, we have f as a field, okay, it's a obvious variable to choose. Okay, so let's say there's a space that we are going to define. We are now going to design rules for something called a field. And this field is not very different from what might come into your mind when you are thinking of a real field, which is composed of real coordinates. What we are going to do is we are going to build up a continuous, in a sense, a continuous field consisting of these numbers. And we'll use 9 rules 4 on addition, 4 on multiplication, and 1 combined rule. Okay. So let's first discuss the rules. So F will be that field, but I'll come to that. Let's discuss the different rules that we are going to impose. And the first rule is going to be that addition is commutative, which means that if I have x and y as elements of the field, and elements of the field just implies at the moment real numbers or complex numbers. Okay, you don't have to overthink this. So let's say x and y are basically some real numbers for the case. We can just take that as the current example. Then what it means is the addition or the order of addition is not important. So you could have done y plus x also. Okay. So this rule is valid for all x and y in F. You can also write this as for all x comma y in F. Yeah. If you want to use a slightly more mathematically sophisticated language. Okay. So I'm not going to repeat this again and again, but x and y are basically in F. Similarly, the other rule, so we said we'll set up 4 rules for addition. The other rule is going to be addition is associative. Which means that if I have 3 numbers, x, let's say we have number y and z, and I add them together first, then I could have just done this. Okay. 3. There is a unique element which we will call 0 in F, such that, okay, so such that, I'll just write it down right now, but later on such that can be just written as ST, that such that x plus 0 equal to x, again for every x in F. Okay. Fourth and the last rule for addition, and that is for every x in F, there corresponds a unique element minus x in F, such that x plus minus x is equal to 0. Okay, now let us set up the rules for multiplication. So we have done with 4 rules. Okay, so now we will have 4 rules for multiplication, and well, no surprises here. We are going to follow the same order. So we are going to say, okay, multiplication is associative. X, that which means xy is equal to yx. Similarly, I'm sorry, I have made a mistake. Multiplication is commutative. Sorry. And the next rule is going to be multiplication is associative. And that is going to be xy, and again the order is not important. I can do this first, and again this is valid for all x and y in F, right? So now here we will have an equivalent of this particular rule. There is a unique element 0, but when it comes to multiplication, the unique element is 1. Okay, because so for each x, there is a unique for actually all x. Okay, sorry, rather say there is a unique element the unique element called 1 such that x into 1 is equal to x. You can probably recognize this is these are all the operations for your real field, right? And wait a second, this is 7, we have 8, sorry. So this should have been 8. With 8 we will be done. So what did we have when we are doing addition? We used it to define something called minus x. Okay. So here what we will do is we will use this rule to define something called 1 by x, or the inverse. Okay. So for each x there exists a unique element (1 by x) such that x into 1 by x equal to 1. And then the ninth rule, which is a combined rule, will say that multiplication distributes over addition. Which means that if I do x, y plus z, that is the same as x, y plus x into z. So with all these different operations, okay, so we have defined 9 operations for us. Okay, starting from operation 1, 2, 3. Oh, I changed the format 4, 5. Sorry, I was using Roman 1, 2, 3, 4. Maybe I'll just rewrite this as 1, 2, and then 3. Okay, so I tend to do this sometimes. I tend to change variables while writing. In a class, it's easy for people to stop me and show me that I'm going wrong in this way. But unfortunately, there's not much you guys can do, and I have to understand this myself, otherwise, yeah. Anyway, okay, so I'm speaking to myself right now. Okay, so with all these different operations, this set F is going to be called a field. Okay. And this field is going to be important because we will use this field to help us define what is called a vector space. Okay. And we will be using very similar rules when it comes to vector spaces. Okay. So today I will end it here. And the next time we will go into vector spaces. Okay. But do remember, I had in the first part of this lecture 2, I had given you a couple of problems involving fluid statics. So please do look into them and try to solve them. We will also discuss the solutions to them in the next class. Okay, great.